Greetings. We're going to do a little video on the discussion question about average body temperature. Okay, a couple things about hypothesis testing before we get started here real quick. Is that hypothesis testing is a fundamental to any elementary stats course, and it's something that we really want to understand. But typically in a course, in a statistics course, you are given summary statistics. You are given the mean, the standard deviation, the sample size, or something of that nature. Well, that's not how it's done actually out there in the real world. In the real world, you won't be given the summary statistics, you'll be given the raw data. And so when we go to conduct a hypothesis test with raw data, that's where in our studio have their strong suit, because it's a real world tool. It's used or designed to be used in the real world. So we're going to go ahead and run this test, and it's going to have summary statistics, and we're going to have to do some of the calculations by hand. But when we have raw data, those calculations will be done by R. R will do them for us. Now, there's a really good example in the lab, I believe it's lab 7, about how to actually go in and run a hypothesis test with raw data. It's the one on miles per gallon. So review that one if you want to see how you go about and do a hypothesis test with raw data. This one is going to be how do we do a hypothesis test for a single mean using summary statistics. Okay, with no further ado, let's go ahead and get into it here, okay? So in this particular one, let's just get to the right slide here. There we go. A study was conducted to test the hypothesis that the average body temperature of a human is 98.6 degrees Fahrenheit. We're assuming a healthy human. The researcher believes that the average body temperature differs from what was stated, the value of 98.6. Okay, so they want us to state the null and the alternate hypotheses symbolically. And they want us to do, in other words, they don't want us to say the average body temperature is 98.6 or the average body temperature is not 98.6. In other words, they don't want the null and the alternate written in English. They want it written in Geek. They want it symbolically. So let's go ahead and do that. Let me get my pen out here. And so that says that the null hypotheses would be that the mean is as stated. It's 98.6 degrees Fahrenheit. Now remember that the alternate hypothesis, H sub A, is always going to be the researcher's hypothesis. And our researcher here thinks that the body temperature differs from 98.6, right? Notice the word differs right here. That's important because that tells us that means that mu is not equal to 98.6. If he had said it was greater than 98.6, we used a greater than, or a less than 98.6, we would have used a less than. Okay. Now, they didn't ask us to do this in the problem, but let's take a moment once we've set up our null and our alternate hypotheses and talk about the assumptions of the test. We're looking at a test of a single mean here, which means that the test that we're going to run is a t-test. And a t-test has some assumptions that go with it. And again, one more time, why did I know that I'm running a t-test? Because I'm running a test about mu here, about a single mean, okay? And since I have a single mean that I'm testing, I'm going to use a t-test. As it turns out, as we'll see in later work, if we have two means, we'll use a t-test also. But if we have more than two means, we're going to use this really cool thing called ANOVA. All right, anyway, let's get back to the test at hand here. So a couple of assumptions that we need to check. We need to check independence, and we need to check normality. All right, so in the case of independence, we can assume that we're going to have to assume that our researchers did a good job. So in other words, they did a good job of getting a random sample, and since they did a random sample, we can assume independence between each of the samples, and we can also assume that we sampled less than 10% of the population. As we'll see in the coming up here, they sampled 35 people, which is going to be much less than the 6 billion Homo sapiens that are living on the planet right now. Okay, the second assumption that we have to assume is normality, and as we'll see in the next slide here, is that the sample size was n was equal to 35. So since we have a sample size of 35, the central limit theorem is going to kick in, and we know that the distribution of x bar is going to be approximately normal. So since the distribution of x bar is going to be approximately normal, the normality condition for the parent distribution is less important. In other words, if we know that we've got a large sample size, not really necessary that we have a normal distribution that we're sampling from for these results to work. Okay. All right, cool. So that's pretty much what we got going in part A. Part B, our researcher gets out their trusty rectal thermometer, oh well, maybe not a rectal thermometer, and gathers up body temperature from 35 healthy subjects and calculates the sample mean to be equal to 98.2 with a sample standard deviation of 0.98 degrees Fahrenheit. So they came up with an X bar equal to 98.2 degrees Fahrenheit, and they came up with a sample standard deviation S equal to 0.98 degrees Fahrenheit. Okay, and they said that their sample size here, N, was equal to 35. So this is what I was talking about in the opening when we started here, that they did not give us the raw data. We didn't have the numbers to crunch and calculate X bar and S. They did that for us. And so now they're expecting us to calculate the t-test statistic based upon the sample. Well, the t-test statistic is equal to X bar minus the mean of the null hypotheses divided by the standard error of the distribution, which is given by S over the square root of N. And there was a fair amount of confusion among folks about how do I go about getting that number. In other words, where does that number come from? So let me back up here to the previous slide. Whoops, went right past it, my bad. And note that this value right here, this guy right here, in fact, let's go back into the same color, let's go red here. This number right here is the means of the null distribution. In other words, whatever the null distribution says mu is equal to, that's mu sub 0. So when we come back over here and do our calculation, I got the right spot here, that's going to be the 98.6. Okay, so let's go ahead and plug everybody into T here. So it's going to be 98.2 minus 98.6 divided by S, which is 0.98 over the square root of 35. And that's going to be my t-test statistic.